So we'll get started. Today we are going to talk about sequential, quadratic programming. The idea today is we will create a, okay, so what are we solving? I want to minimize f of x such that h of x equals to 0, g of x is less than equal to 0, x is in Rn, and the idea is I'm going to create a penalty function p of x, max of 0, g1x, grx, absolute value of h1x, absolute value of hm x, and then I minimize f of x plus c p of x, where x is in Rn. Okay, so this is the problem we want to solve. In the previous lecture, I had mentioned, and we didn't prove it, but we mentioned that if C is sufficiently large, and if X satisfies X star, lambda star, mu star satisfies the sufficient condition, and X star is regular, under those circumstances, the argmin of this is the same as the argmin of this particular problem. So that was something we talked about in the previous class. I just told you the result. So today my goal is twofold. The first thing that we will do in the next 20 minutes is to try and prove this particular result only for equality constraint without the inequality constraint. And then we'll try to figure out what is the descent direction for solving this problem, because remember, this is a non-differentiable function. So we don't quite have we can't just take the derivative and for this particular function, because the derivative doesn't exist, because it's a whole bunch of maximum of a whole bunch of functions, and including those, some of those functions have absolute values associated with it. So that becomes a problem. Okay, so let's try to figure out why argmin of this is also equal to argmin of this. I'm going to erase the gx less than equal to 0 condition for now, and I'm just going to look at h of x equals to 0 condition for the time being. Okay, any questions so far? Yes.
Why do we put the absolute value around the h of x?
Why did we put the absolute value? So remember, h of x has to be equal to 0. So ideally at x star, p of x should be equal to 0. The penalty should be equal to 0. So if each of these terms are negative or 0, we are fine, because 0 is, we are maximizing with respect to 0 comma each of these inequality constraints. Each of them have to be less than equal to 0, so the max will always be 0. Now absolute value of, so if we only put h1 of x, and h1 of x tends to be negative, then for some reason the penalty, I mean not for some reason, but because it's max of 0 comma a negative number, the penalty will be 0. So you're not really penalizing the fact that it's violating the constraint, which is h of x should be equal to 0. So penalty should always be equal to 0 at the optimal solution. Yes.
Why is it called quadratic? Does that require fx?
No, of course, all of these functions are infinitely differentiable for the purpose of this class. But when we get to the descent direction of this, you will see that it becomes a quadratic program. So in order to find the descent direction in this particular problem, you have to solve a quadratic program to get a descent direction, and then that's how the algorithm proceeds.
If we are in the feasible sets, then p of x is 0.
P of x is 0, yeah.
But maybe I'm thinking like maybe we are not in the feasible sets.
Right.
There's something like less than f of x.
Yeah.
Start in this case, and so it kind of compensates for not being in that feasible set.
That's right.
I'm thinking is how.
That's exactly what the idea is. So I'm going to penalize if I'm outside the set. But as soon as I'm inside the set, the penalty function will be 0, and then I'm just minimizing the function without any penalty. Okay. So, I mean, think about it from this particular perspective. So, this is my h of x equals to 0 manifold. This is my g of x less than equal to 0 region, all of this part. And so I could have a point xk which is outside the set, or I could have a point xk plus 1 here. And in both these cases, the penalty is positive. P of x is positive. So I'm penalizing these points as long as they are outside the set. Now, as soon as I reach this point, xk plus 1, the penalty becomes equal to 0. Okay, because h of x equals to 0, so all of these are 0, and these terms will become less than equal to 0. So the max will be 0. Yes.
So this method only applies to where fx can be defined outside the set.
Fx is always defined over the entire Rn.
Oh,
Right? So this function f of x is defined over the entire Rn. Right? So typically, let's say we are picking half of x1 square plus x2 square, then it's defined everywhere. Now, of course, if you have something like log of x1, now it's not defined for x1 less than equal to 0, right? So in those cases, this x will not be in Rn, it will be x strictly greater than 0. That creates a bit of a problem, but we are not going to consider all those problems. For instance, you can have something like x greater than epsilon, greater than equal to epsilon. Now that becomes an inequality constraint, and then you can try to solve the problem with that inequality constraint. But it's still, you want function f of x to be defined everywhere. Any other question? Okay, wonderful. So I'm going to erase all of this, and I'm going to consider the case where h of x is equal to 0, because the proof there is somewhat easy to understand. And the goal is to prove that the argument of this is the same as argument of the penalized function. So let's consider the following problem. Minimizing f of x such that h of x is equal to u, and let's say the minimum value is given by pu, and assuming that it all x star lambda star satisfies second order sufficiency condition, regularity, and all of that stuff, I can apply sensitivity theorem. We didn't prove the sensitivity theorem in the class, but I hope all of you remember the sensitivity theorem. So I can apply this to show that P of u equals to P of 0 minus lambda star transpose u plus half u transpose second derivative u. So I'm using alpha bar. I probably shouldn't use alpha bar. What should I use? Maybe I'll use beta. So beta is something between 0 and 1. Okay, so this is equality because I'm not writing small o of u term outside it. So this is the mean value theorem that we are using, and so P of u is equal to this particular term. Okay. Okay, perfect. So I want to show. Let's consider the following problem: x x minus x star less than epsilon f of x plus c p of x. Well, I need a lot of space, so I'm going to erase this and write it here. So I want to minimize in the vicinity of x minus x star f of x plus c p of x, which is minimize okay. So I have this. What I'm going to do is I'm going to write this as I want to minimize over all u. No, I have to change the order. I have to define a set first. So let's call u of epsilon is the set of u such that h of x is equal to u x minus x star is less than epsilon. So I've defined this set, and then I can write the same thing as minimize u in u epsilon, minimize okay, wonderful. So, so what did I do? So I considered the set of all u that is achieved by the points in the vicinity of x star. So I considered that set, I named it as u epsilon. Now I'm minimizing over all u epsilon such that h of x is equal to u. And because I'm doing the same thing here, uh, uh, so because there is this, so I'm considering all of h of x equals to u, and then I'm minimizing over all u epsilon. So the two expression, this expression and this expression, is going to have the same value. So this is actually an equality. And that's because I'm setting h of x equals to u, and then I'm minimizing over all such u. Okay, so both of these will have the same value. Now, one thing you will notice is if h of x is equal to u, I can actually write it as absolute value of ui, right? Because now I have an equality constraint here. And now this is really a very cool expression. It's cool because in the first minimization, I'm minimizing only with respect to x, and the second term doesn't depend on x. So I can just consider this particular problem I can substitute this. So what is this problem equal to? This problem is the same as this problem. Okay, these two problems are the same. So I can actually replace this inner minimization with P of u, and P of u is given by this expression. So I can actually replace this term in the box. I can replace it by this particular expression. Okay, is that idea clear? So I have this minimization. I split it into two minimization. Turns out that the inner minimization is the same as this problem, which is the same as this particular expression. And the outer one depends on just ui. So this particular function just depends on ui, so it doesn't participate in this inner minimization activity. So what I have is min over x minus x star less than epsilon fx plus c px is equal to min over u in u epsilon p0 minus lambda star transpose u plus half u transpose second derivative u plus c max over I absolute value of ui.
What was the point that you were trying to say? In the rectangle, what we do, minimization of the x.
Yes, so I have I'm minimizing in the vicinity of x star such that h of x is equal to u. That's the same as minimizing f of x such that h of x equals to u around the optimal point, right? And that's equal to pu. We know that to be true. And that's given by this expression. Yes, please.
So what we did was transforming from x dependent to u dependent, where
Yes.
u is constrained.
Absolutely. Absolutely. That's exactly what we did. So, you know, we did in integrals and stuff, you've heard about change of variables, right? So what do you do in change of variables in integral? You basically change the variable and then you rewrite the integral in terms of the new variable. So what I did was exactly the same. So I was initially solving this minimization over x. Now I'm minimizing over u. Okay, so it's a change of variables, but from an optimization perspective. Anything interesting that you see there? So I see something interesting here. This is a constant. It doesn't depend on u. This term depends linearly on u, and this term depends linearly on u. This is a quadratic term on u. U is supposed to be small, so this term is supposed to be order of magnitude smaller than this term and this term. So all we have to do is think about what exactly is the C max ui and lambda star ui. What does that give us? So let's assume that C is greater than equal to summation lambda I star absolute value plus gamma. Gamma is greater than 0. Assume. So then what is C max ui I minus summation lambda I star ui? How can I simplify this? Okay, so C is greater than this, so let me replace C by summation lambda I star plus gamma absolute value. Each of this is positive number, so this is positive, this is positive. I'm doing max over I ui. This is greater than equal to gamma times max over I absolute value of ui. Okay, so this is, so lambda I star max of ui is greater than equal to lambda I star times ui. I'm doing the, and there is a sum here, sum over I here, and then there is a sum over I here, and this gamma term is the hanging term. It's not participating in this greater than equal to sign. So what I have is gamma times max over ui. So I can write the same expression. This expression can be written as minimize u in u epsilon p0 plus gamma times max of I ui plus half u transpose so this is small o of u, and so this is the dominant term. Okay, so what does this mean? Okay, so let's think about it. This matrix could be positive definite, negative definite. It can be any symmetric matrix, right? It doesn't have to be a positive definite matrix. So I know that this term, this u transpose this matrix times u, this could be positive or this could be negative. I don't know. But this is a very small number in comparison to this number. And this number is always positive for all values of u because I'm taking max over ui and then I'm multiplying it by a positive number. So in particular, this particular term, this whole thing is greater than equal to p of 0. What does that imply? The optimal solution is u equals to 0. Because this objective function is minimized when u is equal to 0. And u equals to 0 is part of this particular set, u epsilon. Right, so what I've shown is that this function in the box is greater than equal to p0 because this term is positive, this is positive, it could be positive, it could be negative, but this one is way bigger than this particular term. As a result of which this whole function inside this box is greater than equal to p0, but guess what? If I pick u equals to 0, this p0 is achieved because this term is 0 and this term is 0. So I can actually achieve the minimum value by picking u equals to 0, which means that the optimal solution for this particular problem is actually p0, which is minimum of fx such that h of x equals to 0. So if I'm minimizing this function fx plus cpx, I'm getting the same value as minimizing the function such that h of x equals to 0. So what did we prove? We proved that If I'm solving this particular problem, the penalty, the original function plus penalty, unconstrained, what I get is a solution to the original constraint problem. Right? That's the origin of this penalty method. Okay, so we constructed a penalty function such that the unconstrained problem has the same solution as the constrained problem. Yes.
But it's only around the optimal set.
So all local minima. So it doesn't matter which local minima x star you pick, this holds for all local minima. Okay. All right. Now the question is, great, I've been able to identify this function, and so now I need to figure out what is the descent direction of this particular function. Okay, any further questions on this? Yes.
Here we stated that yes, that rectangle equal to the P of U, but here like what is set under min? I mean, there's nothing but is that is it x in Rn?
Yes.
But we have that x should be in the vicinity of x star.
That's right.
So is that, are we constraining P of U to that?
So remember, when you are trying to solve this problem from an algorithmic viewpoint, you can only get to a local minimum.
Yes.
So you can pick any of the local minimum x star, and that will be a local minimum to this problem. In particular, if you pick the global minimum of this particular problem, you can have the global minimum here as well. But it's going to be an unconstrained. So remember, it's a solid ball. You're trying to come up with the whole reason for picking this particular ball around x star is so that you know that u is also very small, right? So all of these terms will become very small. So all of this condition, this dominant term and then small o of u, all of that is justified. So what we are doing is a local analysis, not a global analysis. But you can do the global analysis, you figure out x star, and then you do the local analysis around x star, right? So that's what we are trying to do here. Okay. Any other question? Wonderful. So let's look at the algorithm, and I'm going to make another small change. Now, so now I'm going to solve the problem, minimize f of x such that h of x is less than equal to negative h of x is less than equal to 0, g of x is less than equal to 0, and then I'm going to define g0 of x equals to 0. It's a function that's identically equal to 0 at all x, and I'm going to write g0 of x is less than equal to 0. So I had the original problem, now I'm transforming the problem so that I only have inequality constraints. Okay. So now I can write the penalty function max of g0 of x, g1 of x, gr of x, h1 of x, hm of x minus h1 of x minus hm of x. Does this make sense?
So we need to put 0.
G0 of x is 0.
Oh.
Okay, so I didn't put 0 here because G0 is equal to 0. It's just to make things easier to write. Yes. G0 of x, yeah.
If it's less than equal to 0, then
It's always satisfied.
oh,
G0 of x, if I pick it equal to 0, it's always satisfied. Okay. So I'm going to write a whole bunch of equations. So I'm trying to show you that even if we consider only inequality constraints from G0 all the way to GR, I can subsume problems of this type by just replacing all the equality constraints with inequality constraints. Okay. So from now on, for the purpose of the algorithm, I'm just going to assume that we only have inequality constraints because I can convert my original problem into an inequality constraint problem. Awesome. So I'm solving the following problem. I want to minimize f of x such that g of x is less than equal to 0. And the goal is find d in Rn such that f of x plus d plus c p of x plus d is less than right. This is how we find the descent direction. If it was differentiable, life was easy. Now we are in a non-differentiable setting, so life is a little bit difficult. Okay, so what we need to understand is how does this function change as I add a small perturbation d to my x. So I need to figure out what this thing looks like. So I'm going to introduce a notation j of x, j in 0 to r, such that j of x equals to px. So I picked all of the active, well, I don't want to call it active constraint, but this is somewhat similar idea. So I look at the penalty at x, I'm standing at some point x, I calculate the penalty. I look at the values of gj's that is equal to the penalty, and I'm calling that index set as j of x. And j goes all the way from 0. Remember, g of 0 was equal to 0. So j goes all the way from 0 to r, all the possible inequality constraints. And if I have equality constraints, I can just convert all of them to inequality constraints and increase the number of r that I have. So that way I can cover the entire set of constraints. Okay, so what is f of x plus, sorry, f of x plus alpha d plus c p of x plus alpha d equals to f of x plus alpha gradient fx transpose t plus max over all j, sorry, c max over all j gj x plus alpha d. Alpha is small, d is small, so I can write it as f of x plus alpha gradient fx transpose t plus c times max over j in jx gjx plus gradient gjx transpose t alpha plus small o of d term. Oh, I did not write plus small o of d terms. Okay, so what is happening here? There are a bunch of indices at which gjx equals to px. What happens to other index? So j not in j of x, this is strictly less than p of x. Okay, so I perturbed by alpha d amount. I know that only the one in j of x will actually lead to the perturbation. The other ones where gj of x is strictly less than p of x, those will not contribute to this maximization operation, right? Okay. So if I pick what is theta of c? Okay, so I'm going to define theta of c x d as max of gradient fx transpose t plus gradient gjx transpose t. This is j in jx. So these gj of x, they are all the same as p of x, right? So these gj's are all constant because I'm picking j in j of x. So this is all constant, so I can pull that constant out. Now my maximization is only over gjx transpose d, because I don't know which of these is going to be positive, which of these are going to be negative, right? These are all constant. Remember, these are all constant, that term. So I can pull that constant out. I can collect this gradient of fx transpose d term. So this doesn't depend on j, so I can push it inside this maximization operation. So what I'm doing is I'm going to write this expression as f of x plus c p of x plus theta c x d plus small o of norm of d. Okay. Is this expression clear to everyone? Why did I get this expression? So these are all constants. I pull the constant out, set it equal to p of x because they are all equal to p of x. This one is this one's something that's dependent on d, but it's constant, doesn't depend on j. So I can push it inside, and then I get theta c of xd here. These terms are linear in d. This is, oh, there should be an alpha here, right? Alpha here. So these terms are linear in d. This term, let me write it as alpha d. So alpha is small, d is small. So this particular term is negligible in comparison to this term. So what should my descent direction be? What direction d should I pick? So that f of x plus alpha d plus cp of x plus alpha d should be less than this. So remember, this is f of x plus alpha d plus c p of x plus alpha d. What d is reasonable d to pick? in order to make sure that this term is strictly less than this term. This is small, this term should be negative. So pick D. So descent direction D must satisfy theta C x D less than 0. Or in other words, I want max over all j in j of x, gradient fx transpose t plus gradient gjx transpose t. I want this to be less than 0. How do I solve that problem? So now at least I got an idea of what is a valid descent direction. I want to pick a descent direction D such that this max over bunch of stuff is less than 0. What would be a reasonable way to solve that problem? Yes.
If everything is less than the 0 fx, every gj.
No, these are all vectors, right? So these are n-dimensional vectors. So think of this as 1000-dimensional vectors. Okay, so let's say x is in 1000. So this is a 1000-dimensional vector. You have like 10 other 1000-dimensional vectors, and you want to find a D such that this whole thing with this max operation is less than 0. And ideally, you want to be able to minimize. Essentially, you want to minimize D in Rn max over this. So if you're picking the minimizing D for this particular term, it must be less than 0, assuming that there is a descent direction, assuming you're not at the optimal solution. Of course, at the optimal solution, there is no descent direction. Any thoughts? How should I solve this problem? In other words, this is the problem that I need to solve. There is still a little bit of problem here, so we'll talk about it. But let's say I want to pick D sufficiently small that satisfies this, that solves this particular problem. How do I solve it? Well, here is an idea. I can write max of, let's say I want to write max of A comma B, right? I can actually write it as min of C such that A is less than equal to C and B is less than equal to C. So I converted a maximization problem into a minimization problem with constraints. Do all of you agree that this is an equality? So how do I solve this problem? I'm going to write it. This is same as I want to minimize D of, where did C go? There has to be C somewhere. Okay. Please note that there is a C here. Please note that there is a C here. Okay, we didn't carry the C. The C was in the maximization thing, so the C should have been here. There is a C here, and there is a C here. Please make that change in your notes. Okay, so I can do this as minimize D in Rn of C. No, this gradient of fx transpose D doesn't depend on J. So I can do gradient of fx transpose D plus C such that gradient of Gj x transpose D is less than equal to C. Okay. Now this is also somewhat ill-defined problem. This is not the actual algorithm. So why is this ill-defined? I want to find the descent direction d such that this particular term is less than 0. I wrote it in this particular fashion. But remember that we also have a penalty function p of x somewhere, and I want to make sure that uh, the p of x plus this particular term should have over the period of several iterations, this j of x is going to change at every point of time. So I want to make sure that I don't pick the set of indices here that, so at every point of time, this set of indices are going to change. So I want to write an algorithm so that the set of indices remain the same in the constraints. So the other problem is we don't have a second order term here. So typically the d will be negative infinity. So in order to avoid this negative infinity type situation, I want to add a quadratic term of a quadratic function of d here, so that I know that d is always well defined. So that leads us to the sequential quadratic programming algorithm, where we have the following: my xk plus 1, xk plus alpha k dk, and dk equals to argmin d in Rn, gradient fxk transpose d plus half d transpose hkd. Hk is a positive definite matrix. Such that gjx plus gradient gjx transpose d plus c is less than equal to c. This is I also have to put a minimum over all c, and so I have to put a minimum I have to put minimum over all c. J goes from 0 to R. And remember, j equals to 0 implies c must always be greater than equal to 0. That's part of the constraint.
Do we need to switch those arguments?
Should we?
Do we need to have there are two midterms, and then one with respect to xi, and then
Other one is with respect to d. So whenever you have two minimization operation, you can switch the order. You can't do that for min max operation, but you can do it for min min operation. Okay, that's a very good point, but it's an important one. So if you have two min operations, you can always switch the order of those minimization. Important thing to note, this is a scalar. Sorry, this is xk. Yeah, awesome. So we always have c greater than equal to 0. That corresponds to j equals to 0 constraint, and then j equals 1 to r constraints are the typical constraints. This is a scalar dependent on xk. This is a vector dependent on xk. So you have this constraint which is linear in d and c. Remember, you have two variables over which you are optimizing, c and r. So you have two variables over which you are optimizing, and The variables are entering linearly in the constraint. The variables are linear, quadratic, and then linear in the objective function. So it's a quadratic program. So this is a quadratic program. HK is a positive definite matrix. So you have a quadratic program, and at every point of time, at every xk, you have to solve this quadratic program in order to compute dk, and then you use that dk to update xk plus 1 by picking your favorite alpha k, and that's why it's called a sequential quadratic program, because you are solving a quadratic program sequentially in order to compute xk plus 1. Now the problem is, I have just 4 minutes. So the problem is, at the very beginning, you don't have a good value of C, right? So how do you pick a value? So what you generally do is, at the very beginning, you set C equals to 0. Okay, you set C equals to 0, you figure out what the Lagrange multiplier for these constraints are. You add up all these Lagrange multipliers and you add some more positive number to it, and then you pick a value of C accordingly. And then at every few steps, you do the same operation. So because at every point of time your C would be changing, right? Your Lagrange multipliers would be changing. And remember, the C has to be greater than equal to the sum of all the Lagrange multipliers. So at every point of time, you will try to estimate what the Lagrange multipliers are by replacing C with 0. So then this particular term doesn't arise. Solve the problem, get the Lagrange multipliers corresponding to the inequality constraint, sum them up, and pick a value which is slightly larger than the sum and set that value to be equal to C. So that's how you run this particular algorithm. And it's a fairly stable algorithm, as a result of which people in real-time control system tend to use sequential quadratic programming. So where do you have to solve these problems in near real time? So let's say you are responsible for building the wind turbine blades at GE Vernova, where the idea is you can move the turbine blades, you can change the pitch of the turbine blades in order to optimize the electricity generation based on the velocity of the wind. Now, velocity of the wind is a very random quantity. Sometimes the wind is blowing, sometimes it's not blowing. Things can change in a matter of a few seconds. So within a few seconds, you need to compute what the new operating pitch should be. And in order to compute that pitch, you tend to use algorithms of this type. These algorithms would be running on small microprocessors that are at the wind nacelle, the wind turbine nacelle. And so within that nacelle, there will be a microcontroller. That microcontroller would be running this algorithm to solve the problem every few seconds, depending on what the wind velocity looks like for that particular wind farm. Wind turbine. Now remember, wind turbines are not in isolation. You have like a whole, like thousands of wind turbines. So the wind turbine the wind turbine in the front would change the velocity and the direction of the wind for the wind turbine in the back. And that itself changes depending on which way the wind is blowing, right? So sometimes a wind turbine that is in the front would become a wind turbine in the back. So anyways, so those are the cases where you need to run this sort of algorithm. In vehicles, you need to run this algorithm to optimize the energy consumption of the battery, or if you have a hybrid vehicle, you want to optimize how much power is coming from the battery versus how much power is coming generated from the engine. So in all of those situations, you tend to use algorithms of this type to do the optimization. So it's I don't know why people pick sequential quadratic programming, but I know that in controls, people who are building control systems, they tend to use this algorithm quite a lot. So anyways, that's all I have for today. Thank you, and we'll talk about Lagrangian methods in the next class.